Hello friends, I'm Ram Lakshmanan. I'm the architect of yCrash. Friends, in this talk, we are going to be discussing about the 16 artifacts that you want to capture when your container application is in trouble, right? So, here are those 16 artifacts that you want to be capturing when the application is in trouble. Because when you're facing a problem in the container world, you don't know, the problem could be coming from anywhere. It could be because of your application's garbage collection. It could be because of threading issues. It could be because of the containers. It could be because of the network, storage. It could be because of any reason. So here, this is the 16 artifacts. If you have the 16 artifacts, you can troubleshoot most of the problem without having any hindrance, right? So how to capture these 16 artifacts? That's where we are given this. You can see here. There is an open source script called as this yCdata script. So when you trigger this script is going to capture all these 16 artifacts for you. So you don't have to worry about how to capture each one of them separately. This script does the job for you, right? How to run this yCrash script in the container. So you can run it in 3 modes, right? The first mode is you can run the script as a sidecar, as a separate sidecar along with your in your pod. The second one is this can run on the same container where your target application is running, right? It's another possibility. The third one is you can run the script on your host itself, the host in which the container is running. So you can run it in all these 3 modes. And the configurations, how to run on these 3 modes is given here. So you can choose whichever the option you want to do based on your convenience and what is your enterprise security asks you to do. Based on that, you can go for either one of the approach. So, but all the 3 approaches are supported, right? And then the another option is, say if you're running this on a Kubernetes, right? If before you recycle the container which had a problem, you can also run it as part of the pre-stop hook, right? Before you recycle the container, the pod, the script can be triggered so that you can have the 360-degree data captured for you. Okay. So friends, having said that, now let's go into each and every one of the artifact that what we are capturing and how it's going to be useful for you in troubleshooting, right? So the first artifact is the garbage collection log, right? Why garbage collection log is going to be helpful? Why garbage collection log is going to be helpful for debugging for troubleshooting the problems, right? To understand why garbage collection log is going to be useful, first we need to understand what is garbage actually. So what is garbage, right? So some people say my talk is a garbage, but okay, let's leave that aside. So here, let's see what is technically what does a garbage means. Let's say I have my application, my memory is there. Now let's say a request comes. Now in this request, my application is going to create to service this request, my application is going to create objects, right? So let's say there is a sign-on request comes in. Just to service the sign-on request, I have to create, say if it's running on a Java web application, you're creating a servlet object, servlet request object, servlet response object. Now they're going to create a customer object. It's going to have a username as a string and then a password as another string. They're going to create a connection object. And it's going to go to the backend. Backend is going to give you back a result set. It's going to have a list of strings. So mapping them. So even to service a very simple vanilla sign-on request, today our modern application is creating tons of objects. Okay, so now I created all those objects. Now I serviced my request. Now the request is gone. Now what's going to happen to these objects which you created? These objects now, they become garbage, right? Because there is no one referencing it, right? It has to be evicted, it has to be removed from the memory so that the space is created to service a new incoming request. So this is garbage. So how are objects garbage collected from memory, right? For that, let's look at a little bit of the evolution of what has happened in this computing space, right? Developer, it was our responsibility to write the code to evict the garbage from the memory, right? That is, back in C++ days, I write code. So as when I create a new object, once I service the request, it is my responsibility to remove that object from memory. Business applications are pretty complex, right? There are multiple use cases, there are multiple scenarios. So for every use case, whenever I create an object, I have to make sure I remove them. Even if I miss in one small use case, then those objects are going to start to build up in memory, and then it's going to create some memory leak, and then application is going to crash. So back in those days, the memory leak was a little bit more pervasive than what we are encountering right now. So Java, when it came in 1995, at that point it told, hello developers, you guys don't worry about garbage collecting these objects from memory. You only take care of creating the objects. It is my responsibility as a runtime to go ahead and reclaim the garbage from memory. You don't worry about it. I will take care of it. Developers, we all loved it, right? We are all kind of we like when someone does our job, we really like it, right? That's good. And management loved it because there's a less memory leak, right? So far so good, right? With this automatic garbage collection, right? Yes, it is good, and that's how it should be. But this automatic garbage collection has a couple of issues. What are those issues are? The first one is, when the garbage collection runs, it pauses your application. It stops your application actually. It freezes. So think, because you created all these objects for sign-on request. Now the garbage collector, there's a JVM, is has to check, oh, does this object is referenced by anyone else in memory? If there's no one referencing, then I can go and remove it. To do this, it pauses your application. Even though in this pause can be for a few milliseconds to several seconds, right? We're going to look at it, right? So that means I'm pausing my application. I want you to visualize this, what I'm going to be saying now. Let's say, think about a dream car. What is your dream car, right? So let's say you worked very hard, you saved money, and now you're going and buying the dream car. Now you take the car and you're driving out of the showroom, and now you go on the roads. So you're going at, say you drove for like a 20-30 miles. And after 20-30 miles, in the middle of the road, the car stops. 2 seconds. And then once again it resumes and starts to run. Even though you didn't apply any brake, the car stops in the middle of the road itself. And then it starts to run. And then it keeps going. And after like another 10-20 miles, it's once again stops for a few seconds, and then it starts to go. How will you feel? Right? You will be pretty disappointed. You will be pretty frustrated, right? But friends, this is what Java Virtual Machine is doing. It's not just Java Virtual Machine which is doing it. All modern platforms does this because of this automatic garbage collection. See, you don't see the Java Virtual Machine, right? We don't see Java Virtual Machine. In fact, we don't even see the servers, physical servers. There are a server, within the server there is Java Virtual Machine, and that is stopping. I don't see that, but actually friends, in 2023, after so much modernization, our applications are stopping. It is stopping, right? But even the cars, which was invented a century back, right? They keep running without any pauses. That electromechanical device keeps running, whereas we are pausing, right? Due to this, friends, every enterprise is losing several hundreds of $1,000s, sometimes in millions of dollars. The world as such is losing several billions of dollars because of this automatic garbage collection process. And then the second thing, the second side effect is the CPU consumption. Okay, what happens? Say if your application is having like a 60-70% CPU utilization, probably 30-40% of CPU consumption is done by your garbage collector, because the garbage collector has to constantly keep running. So it runs, so it takes enormous amount of CPU cycles. So it consumes CPU cycles. Recently, even Uber, they were optimizing the GC performance, and they were able to reduce the CPU consumption, which ultimately lowered their cloud computing cost significantly. To learn about such success stories, about what you can achieve by GC tuning, you can look at this success stories link what I'm giving here. But I just want to share with just quickly one success story, and then let's just keep moving. So here is a success story which I firsthand worked on with a very large automobile manufacturer. Right, it's a very large automobile manufacturer. So when they did the GC tuning, look at this average response time. This is what is the customer facing response time. It is 1.88 seconds. When they did the kind of a GC tuning, their average response time was dropped from 1.88 seconds to 0.95 seconds. Like we're talking about a 50% reduction. 50% reduction in the pause time. Not in the pause time, the overall customer facing response time. Because when garbage collection runs, it pauses their application. Who is paying the price for that pause time? So if it pauses, if any customer transaction comes during that time, he's not going to get back any response. When you tune, this response time gets better. That's what has happened. And friends, think about it. We all have been doing programming and the computing for several years now. How many times in our career we were able to optimize the overall application's response time? Right? We might have degraded, but how many times we have optimized? Whereas here, we are able to optimize without touching a single line of code. There is no line of code I have to touch, I have to refactor. Low risk, such a high impact I gain by this. Okay, but what is garbage collection log? Garbage collection log, it shows kind of how long the GC event took, how long it paused, how much memory it claimed. So this is how the typical GC log looks. It's pretty cryptic. So you may want to use one of these tools, is the garbage collection log, to look at it. But friends, garbage collection log is not just important to tune your application performance. It's a very effective mechanism to troubleshoot your problems, right? See, look, this is collection behavior. When you take the log and upload it one of the tool, this is what the behavior is going to look like. You're going to see the request coming, the memory is building up, a full garbage collection event runs, and the memory is dropping all the way to the bottom. And now you can see the request coming, the memory is building up, a full garbage collection event runs, and the memory is dropping all the way to the bottom. I see this beautiful sawtooth pattern, right? And if I put on the bottom line where it dropped, I put a slope. You can see the slope and the black line, it's going at a kind of a 0 degrees, right? Now, progressing, look at this one, this pattern. What is happening here? You can see the request is coming, the memory is building up, and now in a full garbage collection run, it dropped to only to 22 GB. And now it didn't drop. And when the last full GC event ran, you can see it is only dropping all the way till this 32 GB. See, initially it was 22 GB, now it is 32 GB. Now if I put a slope, this slope is going at 15 degrees, right? So this is indicating that this application is having an acute memory leak, right? It's not very aggressive enough. It has a small memory leak which is going on, right? Now, if this continues, this is how this behavior will look like. You can see, now initially it was here, when the full garbage run, it was at 4 GB. Now as time progresses, not able to come down. After a point, you can see this garbage collection is running, the red triangle is running, but the memory is not coming down. And friends, even when one red triangle, that is even one full garbage runs, it consumes enormous amount of CPU cycles. And here if you can see this red triangles is constantly keep on running, that means it's saying this application is consuming enormous amount of CPU cycles. It's consuming enormous amount of CPU cycles, but the memory is not going down. See, sometimes you might have experienced this behavior. You might have deployed your application in production. All of a sudden, the CPU started to spike to 1900%. You didn't do any code deployment. You didn't make any flag setting changes. No changes were made at the back end, but all of a sudden the CPU starts to go 9900%. It could be quite likely that this full garbage collection is starting to run like this. Right? And friends, the one sad, unfortunate thing is we get out of memory error only when we reach this end point, when we reach the ceiling limit. Right? That is a problem. And also the alarms, the observability tools, the monitoring tools, what we have, they raise alarms only when we hit the ceiling limit. But see, even the several minutes earlier, this garbage collection has started to run. If we look for this micrometric, this garbage collection behavior, several minutes ahead before you get an out of memory error, we can predict it. We can detect it. Right? That's what it's indicating. Okay, once you have this kind of a behavior, what you want to do is you want to take a heap dump from the application, and then you want to troubleshoot what is triggering the memory leak, which we're going to be discussing in next few slides. Okay, now let's move on. The next important artifact that you want to be capturing when your application is in trouble in the continuous world is the thread dumps, right? So what is a thread dump? How does a thread dump look? So this is an anatomy of a thread dump, right? Look at this. Here it prints at the very top what is the timestamp in which thread dump was taken, and then here it shows whether it's what type of machine from which it was collected, with 34-bit JVM, 64-bit JVM, and what it is. And friends, all our applications have hundreds of threads, right? All applications have hundreds of threads. Each thread would have like its own segment. Details about one particular thread is going to be there. Like this, if you have hundreds of threads, you're going to see the hundreds of segments reported in this thread dump. Let's look into the details of this. Okay, see, it says what is the name of your thread, what is the priority, what is the ID, and what state it is, and all this information there. But the most important section here is basically number 7. This is nothing but your application's stack size. Sorry, the code path, the stack trace. It shows your application, the threads, code execution path. You can see the thread started at the thread.run method in this class thread.java, and then from there it went on to move to execute this particular method, thread pull executor, worker run method, and from there it on to execute this run worker method. It progressed and keep on executing, and here it shows the final line of the code that it was executing when the thread dump was capturing. You can see it was executing the set connecting flight method in this class itinerary segment processor on line number 380. This is what it's executing. This is what it's telling. Friends, with this information, this looks like pretty rudimentary, very easy to know, but with this information we can troubleshoot so many threading related problems, so many application problems. So here I have gotten a couple of real world examples of how this thread dump facilitated to troubleshoot a couple of problems, right? So we'll look at it. And before I go on to look at it, you can use the thread dump tools, right? The thread dump to be analyzed through your text editor. You can open it up and look in a text editor, and you can do it. But it's a little bit tedious, but it's still doable. Otherwise, you can use these kind of tooling solutions. Like these are some of the tools which you can look at using for troubleshooting your thread dumps. Okay. Now let's look at some sample problems, case studies, how this thread dump was helpful in solving some of the critical problems in major enterprises, right? Okay, friends, this problem happened in a middleware deployment of a very major financial institution in North America. So all of a sudden, this middleware became unresponsive. We don't know why it became unresponsive. So when the script was triggered, it captured this 360-degree data, and this thread dump helped us to rescue the problem, helped us to identify and pinpoint the problem. Let's look at the thread dump. What are the thread dump we captured? That's what we're going to be looking at it right now. Let's look at it here. So here is the thread dump of the financial institution middleware deployment, which had the problem, right? See, you can see at the very top it prints, this analysis says, what is the total thread count and what thread states they are. So this application is having like 1,859 threads, right? Which is pretty significant high number of threads. Typically this application has only like a 300 or 400 threads, but now it is having a very high number of count of threads. Okay, so now progressing, and there is multiple sections, but let's look at the section which is of interest. Here you see there is a section called threads with identical stack trace. So what this section does is it tries to group the threads which have the exact identical stack trace and reports its count. Okay, here you can see there is like 1,706 threads, right? 1,706 threads. They all have this exact same stack trace. If multiple threads in your application starts to exhibit a same stack trace, then that is an area of concern you want to be looking at. Because say only when there is a problem, all the threads are going to be getting stuck. That means their code path stack trace is going to be more or less. You want to see if the multiple threads going in, if multiple threads are exhibiting the same stack trace, you want to investigate it. So here is that. Here I am able to see it now. What's going on? Here you can see this. There is 1,706 threads. All of them have the same stack trace. You can see it is originating from Oracle JDBC driver. Right? It's originating from the Oracle JDBC driver. This is a middleware platform deployment which is talking with multiple system of records. So this application was talking with close to 100 system of records, SORs. One of the primary system of record is an Oracle RAC cluster. right? So the Oracle, the database vendor, they gave a flag called ONS, that is Online Notification Service. So they asked this middleware team to enable this flag, ONS flag, to be true. So when you set this flag to be true, what will happen is, in the Oracle RAC cluster, it's a multi-node cluster. If any one node has an outage, if it has an issue, automatically what's going to happen is that the traffic will not be sent to that node which is having an outage. Rather, the very next transaction will be sent to the other available nodes in the cluster. So this will increase the availability of the RAC cluster and the transactions of the middleware transactions ultimately. So this middleware team enabled the flag. When they enabled the flag, what was happening was, for every call that was going to that RAC cluster, a new thread was spawned. Right? That's what we are showing you. Like 1,700 plus such threads were created. That kind of thread leak. And now when this track trace was taken and it was reported to the vendor, the Oracle, they acknowledged, oh, yeah, sorry, this is a bug. And then they fixed it. They made a new JDBC driver release. And once it was installed, then the problem went away, right? So this is one classic example where how the thread dump can be of helpful. Okay, friends, now let's also look into another problem. So this was an degradation in response time happened in a very major travel application, right? So this travel application processes like almost 70% of North America's overseas ticket reservation, right? If you make an airline ticket reservation, most likely it's going through this platform, a leisure travel platform, right? So this application, all of a sudden there was a degradation, the response time was happening, okay? So at that point this dump was captured. At the time, the YC script was ran, and it captured that 360-degree data, and here also the thread dump came to rescue. But friends, before we look into this actual thread dump, let's look at, well, there's one interesting state, a thread state. Every thread can be in one of the 6 thread states. One of the interesting thread state that what you want to be looking at when analyzing a thread dump is the blocked thread state, right? So when does a thread get into a blocked state? Right? Let's look at it. So let's say here is my code. So I've written something like public void synchronize get data, make database call. Right? Here it is. So here there is this thread 1. Right? Thread 1 it comes. What is a synchronize method, friends? First of all, what is a synchronize method? Synchronize method means only one thread will be allowed to enter into that method at any given point in time. Right? If any threads try to come in, it's going to put in the blocked state. Right? Now let's say a thread 1 comes, it checks, oh, there is no other thread is executing this method get data, so now it will be allowed to go inside. So now it has gone inside, and now let's say this thread 1 is now executing this make database call. Let's say this database call takes something like a very long time to complete. Maybe it's a slow running query. At that point, let's say if another thread comes, thread T2 comes, this thread will be put into the blocked state. Thread is going to put in the blocked state. What if thread 1 still didn't complete, still taking time? Say at that point, if other threads are starting to come, another thread they start to come, they all also will be put in the blocked state. So like the threads will get built up. Eventually, there is going to be a degradation in your application response time, right? So equipped with this knowledge, let's now look into that actual thread dump data which was captured. Yeah. So friends, here is a thread dump. There's multiple sections. In the interest of time, I'm not going to go into each and every section. But however, look at this. Here, there is a section called, this is a section which paints a kind of a transitive dependency graph of blocked threads. When a thread gets blocked, this transitive dependency graph is painted, and it kind of shows, here is the class and here is the method which is blocking 646 threads, right? So here is all those 646 threads which is being blocked by this particular thread. So these are all the victim threads that are being blocked by this particular guy. Now let's look at the stack trace of one of the victim threads. So now I'm clicking here. You can see the thread, this victim thread, it started out on this method, a thread.run, the very original method, and progressed along. And now look at this, friends. This thread is trying to invoke the method random UUID method, which is in this Java util UUID package in the class. So what does this method does? This method is going to random number, a random UUID, right? And friends, this method a lot of developers doesn't know, but this is a synchronized method. It is part of the JDK library, but it's part of, there's a synchronized method. And only one thread is going to be allowed to enter. So there's a victim thread. It looks like someone thread is executing. So you're saying, see, it is saying it is waiting to obtain this lock. So it has put into this blocked state. This has gone in block state. Similarly, like all other threads are here, are put in the block state. So this is the culprit guy. This is a culprit thread. Right? Let me click here. You can see the thread, it started out, it progressed. Now it's saying random UUID, right? When it does that, here, since the first thread, it was able to obtain the lock, and now it didn't come back. It is taking very long time to come back because, friends, what does the JDK, this random UUID does is, it doesn't generate a random by itself, rather it delegates a call to the underlying operating system, underlying kernel, to generate the random number. So what the kernel does is, in the kernel there's a concept called entropy. So what is entropy? The kernel needs some noises to generate this random number. So it looks for this mouse movements, it looks for keyboard strokes, or the noises made by the device drivers to generate the random numbers. If there's a lack of entropy, then a random number generation is going to slow down. So that's what was happening. Because it was slow and what was happening in the kernel, it couldn't generate a random number, especially because the UUID was a synchronized method. All other threads which are coming behind, they are getting stuck. That's why this application is becoming unresponsive. When this sort of problem happens, what we can do, at the kernel level, you can install some patches so that it can generate, you can install some algorithms so that it can generate random numbers by itself. So that's what we did, and then the problem resolved, and then it went on. Okay. So now, let's keep moving forward. So the next important artifact that what you want to capture when you're troubleshooting the problems in the container applications is heap dump, right? Heap dump is a thing. You have a memory leak or out of memory error. That's when you want to go for capturing the heap dump. And when you capture heap dump, you can use the tools like these are some of the tools which you can use to do the troubleshooting. So now let me open up one of the heap dump which was captured, right? And here, if I can come in here, it shows what are all the any leaks aspect is going to show. Here is a dominator tree. It kind of shows what are all the biggest objects which is there in memory. If you want to click and see, oh this is child element. It has a my map. Now I'm clicking. It has an hash map, right? Here is all the attributes or the values. Yeah, so here I can see, I can click on one of the node, I can see actual data which is present in it. So if there's any memory leak or any out of memory error, you want to take this heap dump and then you want to do analysis. But friends, I want to give you a warning. It has multiple sections, but in interest of time, I'm not going to go into the details. But friends, I want to give you a warning, right? In this, all the artifacts that we capture, heap dump, in the 16 artifacts that have been captured, the heap dump is the only intrusive artifact. That means the entire script completes running within 30 seconds. But if you take heap dump, it's going to take a little longer. How long? It's going to be depending on how big is your heap sizes. So I will not capture heap dump unless it is absolutely necessary, because it's going to stop your JVM. It's going to write that entire heap into disk. It all takes time. It may run for several seconds to sometimes even minutes. So we don't want to do that unless we know it's a memory problem. So by default, this yc script does not capture the heap dump. So only if you pass in flag, explicit flag -ht, that's when it's going to capture heap dump. Okay. So otherwise, what does it do is we can capture what we call as a heap substitute, right? So this heap substitute, what does it do? This is a very lightweight data what it captures. It's not going to give you the actual data which is held in your memory, but it gives you a high-level summary. Oh, this is a histogram. It gives you a histogram of what are the objects which is there in memory, how much size they occupy, and how many number of objects that they exist. Right. So let me see whether I can show you. Yeah, let me show you that how that histogram is going to look like. Here is that histogram. It shows, oh, these are all the objects and how much memory they occupy. I get to see them. right? I get to see them. So this is good enough to give me a high-level flavor of what's going on, right, in the application to troubleshoot. Okay, so we have covered 4 artifacts, right? And now let's look at the 5th artifact which we want to capture when we have the problem, is the top data. See, the top is a very beautiful command which gives you very vital metrics. One of the metric what it gives is, it gives all the processes that is running on that container and what is the CPU and the memory consumption of all the processes running. See, sometimes within my container, my neighboring application could affect my application's availability. What if my neighboring application is consuming an enormous amount of CPU and my application may have a CPU starvation? There's a Splunk, there's a cron job which chew up all the memory, and now my application will have memory starvation. So I get to see all of them here. Not only that, it also gives you other informations like the CPU utilization. The one metric that I really like here is called as a stolen CPU time. Right? There's a stolen time. If the hypervisor is not, if the container manager is not giving you enough CPU cycles to your container and is stolen and given to some other container, then it's going to be reported here, the stolen CPU time, right? Which is very good metric to be tracked and to be aware of. Now, another metric, what I really like in the top is the load average. This load average kind of tells me how stressed out my machine is, what kind of load it is handling. And this data became very helpful in troubleshooting one real problem, right? So this is I want to share this case study, right? This is a very, very major cloud provider. I will be surprised if you won't tell who it is. A very major cloud provider. They were trying to port an insurance company application from their on-prem to their cloud, so that cloud providers professional services team, they were supporting that insurance company to make the pivot. So when they were doing that from on-prem to cloud to their cloud, they didn't. What happened was the on-prem was giving a better performance than the cloud. So they thought it was a garbage collection issue. So they stumbled upon my talk in the YouTube, and then they reached out to me. It's a GC. We looked at GC and it didn't look. It was looking normal. Anything happened. So I told, run this yC script. Let's capture 360-degree data. Let's look at what's going on. When they ran, when they captured, what was happening was data. Right. This is the top analysis report of that application. Yes. So here is that basically the top data. This is just an analyzed result of the top data. You can look at the command line. You don't have to use the tool. You're also welcome to. So here it shows the load average. You can see it's at 100. It's going on something like this. Very high load average. It has been going along, right? And similarly here, so this is the data of one of the node in their cluster which they migrated, and this is another node in the same cluster which was processing. But look at this load average. It is 8, 5, and then 15, right? You can see. So what it is, the one node in the cluster is having a very high load average, whereas the another node in the same cluster is having a very low average. So this was indicating that the traffic was not getting evenly distributed across the nodes. So then when we looked at the load balancing algorithm, there was a glitch in that. Due to that, it was not equally distributing the load across all the nodes. When we addressed that, the load was going evenly across all the nodes. Then the performance characteristic of the cloud deployment was matching their on-prem deployment. So that helped to identify the root cause of the problem. Now I'm moving along. The next data, what is of important or interest is the PS, which is the process status, right? See, the top command, when you execute, it will not give you the complete command line arguments of my application, right? Of all the applications running. It just gives the initial few characters, which is not good enough to identify. I want to see all the commands, all the arguments of the process, so I can really identify. So PS gives that. So marrying the top data with the PS data will help me really know what is the exact process is. Otherwise, I'll just see the initial few characters, which is not going to be helpful. So in that case, this PS is going to be helpful for us. Top-H. Friends, how many of you have used Top-H? See, the top has one secret option that is called as a Top-H, right? When this is going to be very helpful to troubleshoot the CPU spikes, right? So now look at this. You can issue this command, top-h -p process ID. See friends, when we issue the top command, it's going to display all the processes running on the container and what is the CPU and memory utilization. When we issue the top-h -p process ID, it's going to display all the which is running within that process and what is the CPU and the memory consumption of all that within that particular process. So when we execute it, we're going to see like this. Oh, here I see, oh, these are the thread IDs of within this process. And you can see it's consuming 69, 65, 64% of CPU. So then I know I can identify these are culprit threads. And already the thread dump, which we saw earlier, is giving us what is the stack trace in which the threads are executing. Marrying these two data, I can exactly pinpoint the exact line of code, the exact method which is causing the CPU to spike. Right? So I'm saying top-h allows the thread dump. So as a case study, I picked up a real an application, the problem, a trading application, which had a problem, which had a CPU spike all of a sudden. So let's look at the data quickly. So yes, here it is. So here you can see here there is this section called CPU and memory. So here it's printing all the threads and how much CPU it is consuming. Here you can see there's a web container 18 thread, and it is this thread is alone consuming 60.9% of the CPU. When I click on this, here I can see the code path. You can see the thread. It's an IBM application. It started out, and now it's saying this is the method vcachemap.put, which is consuming like 60.9% of the CPU. See friends, the hash map, the data structure, as it's documented, clearly documented, it's not a thread safe implementation. If multiple threads starts to do a concurrent get and put, what will happen is this method will start to go, the thread will start to go on an infinite loop. Even if one thread goes on an infinite loop, then the CPU is going to spike up. Some people say this is a bug, but some people say this is a feature. Because the document is clearly told it's not a thread safe implementation. If you want to go for thread safe implementation, go for an hash table or a concurrent hash map. But I would go for concurrent hash map, which has a more similar performance characteristics, but it doesn't have this infinite thread looping problem. So you can go ahead and approaching the problem like this. Okay. So now the next data, what you want to pick up to troubleshoot is the disk usage. Sometimes due to lack of disk, lack of storage in my container or on the host, if I am not able to write it into the disk, my logging doesn't work, then I'm going to have an issue. My application is on outage. So disk usage is going to be helpful. And the next data is the dmessage, right? What is dmessage? Right? Dmessage is nothing but the kernel log, which will be very helpful to troubleshoot some content. See, this problem or this case study I'm going to discussing. There is this service called as Elastic Beanstalk. It's one of the services from AWS. So the application Elastic Beanstalk is a kind of a containerization service it provides. So this an application which was running on this containerized deployment, it was having an HTTP 502 error. Right? It was getting intermittently. It was not getting always, but intermittently it was getting. Some transactions were getting 502 and some things were not getting. So this is how that the Elastic Beanstalk architecture looks like. So there is at the very front there is an Elastic load balancer, and then so each container will have a Nginx server and then an application server. That's how they are architected. So if you're going to have 10 containers, each container is going to have a new Nginx server and then application server. That's how it is. So the traffic is distributed across all the containers, right? So this is the error we were getting. 502 bad gateway error Nginx. This is what we are seeing in the screen. Right? See the clue here. See the 502 could be thrown because of the Elastic load balancer, or it could be coming from the Nginx, or it could be coming from the Tomcat. But this is a clue that we got. It is thrown from the Nginx. Right? When that yC script ran on that application, you can see this is the dmessage. There's basically kernel logging. right? Here it shows out of memory error, kill this process, kill the Java process. So what was happening, the kernel in the container, it was terminating the Java process because of lack of memory. It is killing the child process. It was killing. But over the container management, the EBS service, whenever it sees the Java process goes down, it automatically restarts it. So you can see the kernel killing it, but the Elastic Beanstalk, the manager, the container manager is restarting it. Killing, restarting, killing, restarting. So the application is going up and down, up and down. So when it's down, if any transaction comes and hits that container, it was getting that 502 error. So equipped with this information, we were able to go ahead and resolve the problem, right? And then the next data, what you want to look at it when troubleshooting is the netstat, the network connectivity, right? This kind of gives me all the IP addresses with whom I'm connecting and what connection count it is, right? If I see some against particular host, there are tools like in this tool and all, you are going to see what are all the hosts to which the connections were made and what state they are. If you see in particular hosts, if the connections are keep on going to the closed state and not shutting down, then that's a concern that we want to be looking at it, investigating and fixing it, right? And then the next data is the ping, right? So through the script you can configure some external hosts, right? And you can say how long is the ping time is going to take, like. So I can configure to external host to some within my data center or outside, or to my backend system of record, and just do a ping and then see how long it's taking. If there is some network issues, the ping is going to catch it for us. And then the vmstat, like I want to see what is my system performance, what is my CPU utilization, what is my swap, what is my memory. I want to take a look at it. vmstat is going to be helpful in that case. And then the kernel parameters, right? So sometimes in the containers, the settings may not be identical of the kernel parameters. I want to see, it may be helpful to compare what is my one of the container setting and other container setting. In case if there's a problem, it's going to be helpful, right? And then application logs. Friend, this is very, very important, because a lot of issues are caused by our application code, and which is going to be logged in the application data. In the container, everything goes away, right? And the container, everything goes away when it gets when it gets shut down, right? So we want to capture them. So the last 5,000, the script can capture the last 5,000 lines of code, and then they can send it to you so that you can look at it, right? And the next is the metadata information. That is what container, what process ID, where it ran, those kind of information is going to be helpful for us. Okay, friends, equipped with this information, right, or with these 16 artifacts, we can troubleshoot most of the problem that is originating in the container world, right? Okay, friend, this what we saw now is a we get a kind of feeling of to go about troubleshooting in the container world. But or if you want to go into the more details, you want to understand more about Java performance and the troubleshooting and in the container world, you may attend my masterclass online. Here is a link I'm given. Okay. Okay, friends. Thank you very much for attending this talk. Thank you, everyone. Thank you.